Good evening, everybody. So, good evening, everybody. Oh, my goodness. Well, thank you all for joining this event. Welcome. I'd like to make sure that everybody that wants one has got a headset. Everything this evening will be in English. But because of the high levels of background noise, we thought these headsets would make it much easier to follow. So if you do want one, just pop up to the table at the front and grab one. He will want your badge in exchange, and you can get it back at the end. So, and to a few people who have headsets on, can you tell me whether it's working? Working at the back? Working at the side? Okay. So, my name is Tom Evans. I work with the Wildlife Conservation Society. The focus of this event is on high integrity forests, often also called intact forests. They are large, healthy blocks of natural forest, free from significant levels of human degradation. And sadly, only a minority of the forests in the world now fit this description. Many, perhaps most of them, are managed and defended by indigenous peoples and local communities. So this event has been organised by Forests for Life, which is a partnership dedicated to securing a future for these forests. You can see the logos of the 5 partner organisations there. This evening we're going to hear from 3 distinguished scientists about the critical role that high integrity forests play in climate regulation. The 3 speakers are going to speak mostly about the role that these forests play in the carbon cycle, which is very, very substantial. I'd like to take a few moments just to mention that these forests also play many other very important roles. For example, they help to regulate the climate in ways other than affecting the carbon cycle. For example, by through the large-scale evaporation of moisture from leaves, which lead to biophysical cooling of the atmosphere, and also drive large-scale patterns of rainfall. And there's a great recent report by the World Resources Institute, WRI, summarising a lot of research in this area, and I'd encourage you to go and take a look at that report on their website. These forests are also critical to maintaining the world's abundant biodiversity, and there are many ways in which the individual species present are important for ensuring the function and resilience of forests. The wildlife need the forests, and the forests very much need the wildlife too. Now, events like this are needed because high integrity forests are declining rapidly around the world. They're not getting the protection that they deserve. To take one example, the area of intact forest landscapes has declined by around 12% in the last 20 years worldwide. There are many reasons, but one key issue relevant to the COP is that current forest and climate finance tends to focus primarily on avoided deforestation and restoration in areas where past deforestation rates have been high. Now, of course, those actions are essential, but alongside them, we also urgently need to invest in securing high integrity forests before threats to them become severe, so that they retain their full value to humanity and to the biosphere. So this has been recognised recently as one of the 6 action areas of the Forest and Climate Leaders Partnership, which was launched last week as a mechanism to help the implementation of the Glasgow Leaders Declaration on Forest and Climate from the COP last year. And WCS and our partners at Forests for Life, many of whom are in the room, are actively involved in the search for solutions to this challenge. I'm sure many other people in the room are too. It's going to need all our efforts and more. So I'd now like to introduce the first of our speakers. Unfortunately, she is speaking remotely, and as the internet connection is slow, she has kindly recorded her presentation. The title is Change and Resilience Across Amazon Forests, and she's also going to give us a brief overview of the global picture. Her name is Dr. Adriane Esquivel Muelbert. She's an assistant professor in global forest ecology at the University of Birmingham and the Birmingham Institute of Forest Research. So Adriane is originally from Brazil, and she investigates how forests, particularly the Amazon, respond to global change. Her work demonstrates how droughts and high levels of CO2 have been shaping diversity and species distributions across South American forests. And more recently, she's been investigating how and why trees die across large geographical scales, a critical issue for all of us. So if the gods of technology are willing, it seems they're not. Please give me a moment. Hello. The video that we set up to work earlier is not anymore working. Yes. Shall I run it again? I do apologise. This was working beautifully earlier. I'm sure it'll be working beautifully again in a few moments. Meanwhile, I'll take the opportunity to introduce our
the carbon cycle, and this is what I want to talk to you about today.
Thank you.
Hello everyone. Thank you for the invitation. I'm very excited to talk to you about the importance of high integrity forests to the future of our climate. Forests are fundamental for our existence in the planet, but also for the future of our existence here. And they play a very important role, both in terms of biodiversity and also for people's livelihoods. But they also have a very important role in the carbon cycle, and this is what I want to talk to you about today. Forests stock large amounts of carbon. We estimate that it's around 400 gigatons of carbon stocked by forests in living biomass, which this is equivalent to 40 years of current anthropogenic emissions. And if you look at this gradient of forest carbon density across the planet, we can see that it's very dark in the tropics. Tropical forests, they are responsible for only 30% of the area, but they stock 50% of the biomass that we have in forest biomass. Forests are also very important for as a carbon sink, so they are not just a pool of carbon, but they also absorb large amounts of carbon. So here you see the balance between the emissions and the uptakes, the emissions in terms of anthropogenic emissions from fossil fuels and land use change, and then the uptake that goes to land and ocean, and the imbalance here, the difference here is what ends up in the atmosphere. Of this land uptake, so 3 in every 10 molecules that go to the atmosphere go to the land, and most of this is absorbed by forests. And if you look at the distribution of it across space, we see that again tropical forests play a very important role as a carbon sink. And the data from forest inventories allow us to estimate that for tropical forests, the high integrity tropical forests, are responsible for 1 gigaton of carbon sink each year. Today I want to talk to you especially about the Amazon. The Amazon is the largest and the most diverse tropical forest on Earth. It stores between 150 and 200 gigatons of carbon, and is responsible for 12% of the terrestrial carbon sink of that land uptake bar that I showed you a few slides ago. And as all the other ecosystems in the planet, the Amazon has been suffering from environmental change. The major source of destruction, the major cause of destruction that is going on in the Amazon is deforestation. And in this work from Gatti and collaborators, you can see the impact of deforestation on the carbon balance. So big emissions from fires affecting the carbon balance across several regions in the Amazon. However, a question that it's the core of my research and of many scientists in my field is trying to understand what's happening to the forests that stay standing. Are they still going to be able to work as a carbon sink? Are the stocks going to be compromised with other changes other than deforestation? So in the Amazon, the major drivers of forest change, the big environmental changes that are going on in the Amazon are droughts. So we had frequent droughts in the last 20 years, in 2005, 2010 and 15. Droughts like these were previously very rare. And then after 2005, which was a big drought, the biggest in the last 100 years, then we had 2010 and 15, so droughts became much more frequent. But also they are now hotter, and the dry season itself is getting hotter and drier, which is a bigger stress for the plants. On the other side, you have the increase in atmospheric CO2 that somehow fertilizes the forest, so stimulates photosynthesis, and also and then also mitigate the effect of drought somehow. So it allows the plant to be less exposed to the drought by not opening so much the stomata, which is the organ that the plant uses to absorb carbon. So it somehow protects the forest from drought. So we have these two different forces acting in different directions and causing change across the Amazon. So how do we then measure this change that is happening, the impact of environmental change on the forest? So there is this big collaborative effort of hundreds of people across the Amazon that have been trying to monitor forests over time. So over the last 30 years, people have been measuring the trees and then going again back to the same place every few years, and identifying which species and understanding how much the trees are growing, which trees are dying, and on what rate, and how much carbon is staying in the forest or how much carbon is being released. And these allow us to get a picture of the trajectory of the carbon balance across the last 30 years in the Amazon, but also a picture of how much species are changing, the climate sensitivity, and the future of the global carbon, the future of the Amazon carbon balance. This is a massive collaborative effort, and it's part of the forestplots.net, which is an initiative that brings together scientists from all over the tropics and also from temperate regions. But here's just an example of the number of institutions involved in this process. And from that data collected by hundreds of researchers across the tropics, we now have a sense of what's going on across the Amazon. So this graph shows the trajectory of the carbon balance across the Amazon over the last 30 years. And what we see here is the Amazon has been working as a carbon sink. So the intact Amazonian forests have been working as a carbon sink. So most of this gray line here is above zero, and we see that this capacity to absorb carbon has been declining over time. So it's getting more closer to becoming a carbon source here. And we also see that those two droughts that I mentioned to you, 2005 and 2010, they have an impact in the shape of this curve. So they bring the curve closer to becoming a carbon source. So here the impact of the two droughts. And a big question is what's happening across the forest. So not just, this is just one picture. This is putting all the plots together. But it is important to understand how the droughts are impacting this forest across the whole landscape. And I want to put forward two messages to you today on the complexity of the system and the resilience of the forest. So the first one is that these forests are adapting to droughts. So looking at the same data, but now focusing on the species and how species are changing, we see that we have more species adapted to drought coming into the system. So more species recruiting every year. And that has been happening consistently across the whole data set over the last 30 years. We also see that dry-affiliated species, so the ones adapted to droughts, are resisting more compared to the wet ones. So we have more mortality of wet-affiliated species. But that's not happening everywhere. That's happening mostly in the dry regions. And this is not happening as fast as the changing climate. So the changing climate is happening much faster than the changing community composition, so the change in species that are there in the forest. And this is because forests are slow systems that take quite a long time. So a tree can live for hundreds of years. So the change in which species are there takes a long time as well. So this is a big open question, is for how long the systems are going to be lagging behind climate, and whether there would be at some point somehow a collapse, or whether they will change very fast at some point as well. Another message I want to put forward to you is that the impact of drought is not happening the same way everywhere. One example of this is that in the El Niño 2015, which was a big dry season. It brought a big dry season to the Amazon, a big drought with very high temperatures. We see here in this in the center of the Brazilian Amazon, in this transect that we have between Manaus and Porto Velho, we see that when comparing the data before and after the drought, we have a big increase in recruitment rate after the drought. And we didn't have any effect on tree mortality. So somehow these forests, on average, they have been benefited by the drought. And apparently this is happening, so this is likely to be happening because of the availability of water in the soil. So the group from Flávia Costa and INPA in Central Amazon is now working on this idea that water table depth can influence a lot how forests respond from climate change. And actually, a large proportion of Amazonian forests are under very shallow water table, meaning they are waterlogged most of the time. And then during a drought, they can be actually released from that waterlog and do better than they would otherwise in a normal dry season. So this is something that we need to understand. What's the limit of that benefit, and what's the impact actually of this benefit across Amazonian forests? And if you look also in terms of mortality risk of death of Amazonian trees, we see that drought-tolerant species tend to do better, but this is only in the south of the Amazon again. So the risk of death, it's bigger in the fringes of the Amazon for trees not adapted to drought. And this again shows this heterogeneity of responses, and show that really is only one region that is majorly suffering from drought across the Amazon. So when we evaluate these big trends that are happening as a consequence of climate change, this heterogeneity may play a big role both in the carbon balance but also in our understanding of the system as a whole. So these highly intact Amazonian forests, they have a fundamental role in the climate target. They are changing, but they are also adapting. And these responses are heterogeneous and depend on local conditions. So really we need to continue this work to be able to understand the impact of this adaptation on the on the carbon balance, but also the impact of these heterogeneous responses in the carbon balance as well. A big vision for the future would be to integrate the data measured in the plots with modeling and remote sensing, so we can get a sense of what's going on across really large scales, and then we can integrate, we can fill gaps in the data from the ground using remote sensing. But the very fundamental data stream that we have here is the data from the ground. This data that is measured tree by tree by different people over many years, so we can see, actually we can get a picture of the balance of the forests and what's happening in terms of carbon and biodiversity. And this data can from the tropics can also be integrated with other global data sets to generate then a live picture of the carbon dynamics. This is something that we are working on at the moment. We are creating this global picture in collaboration between tropical forests and partners from the global north. But there is a big challenge here, and the big challenge is that there is no funding to continue the measurements in tropical forests, and this is compromising our understanding of the trajectory of these systems and how these very valuable forests for our carbon, for our climate mitigations, are going to be impacted by climate change. So I want to raise awareness to that, and with that I would like to thank for watching my talk, and I look forward to the questions. Thank you very much.
So Adriane did say she was going to try and follow this this event online on the streaming, so I'm sure she will appreciate your applause. I'm afraid she's not available to take questions, but we do have two other forest experts here. So if anyone has any questions on Adriane, the points that Adriane has raised, Simon or Nancy may be able to field them. So can I just throw the floor open for a minute, see if anyone wants to ask anything at this point? You'd be very welcome to. Okay, so in that case, with no further ado, let me introduce our second speaker. So Simon Lewis is a professor of global change science. He has led the team that first documented the rainforests of Africa are a globally significant carbon sink, led the team that first mapped the world's largest tropical peatland in the centre of the Congo Basin, bringing it to world attention, and most recently discovered a new tipping point in the central Congo peatlands, which I think we'll hear a bit more about. Simon founded and co-leads the African Tropical Rainforest Observatory Network, AFRITRON, and the Congo Peat Research Network with African colleagues, and he's advised governments in Africa, Europe and North America on forest and climate change. Simon.
Tee up the slides.
Would you like me to?
Yeah, can you, or can you get it on? Hi everyone. Thanks very much for coming at sort of graveyard shift, second week of COP. It's a pretty tough time, I think. You have to start it from the start. Don't start it from there. So I'm going to talk about the Congo Basin and the importance of Congo Basin forests and peatlands. And they are, next, crucially important. Second largest area of tropical forest in the world. Global concentration of species, so very roughly, we don't know exactly, around 10% of the world's species in Congo Basin forests. And crucial in terms of the climate, both for transfer of energy and then in the water and carbon cycles. So the Congo forest generated rainfall is falling in the Sahel, and it's also falling in the Nile headwaters, keeping agriculture going in Egypt where we are today. Next. So I'm going to talk about three things, a bit in deforestation and what's left, and then two scientific discoveries around the Congo Basin. Next. So this is where we're talking about, this area in Central Africa. Next. And this is the deforestation over the last 20 years in Central Africa. So you can see in the Democratic Republic of Congo, you're starting to see some deforestation, but huge areas still without any deforestation and quite far from areas of deforestation. This goes much faster on my computer. And here's 2021 last year, 2020. So I think for our purposes, you can see it's deforestation in the Democratic Republic of Congo, but in Gabon and Republic of Congo, there's been very little deforestation over the last 20 years. And what that shows us is obviously there's different policies are having different impacts across the region, but also there's a lot of high integrity forest left. So there's around 170 million hectares of tropical forest left in Central Africa, and over the last 20 years we've lost about 8 million hectares. 5.9 million of that was in the Democratic Republic of Congo. Next. So just to bring us back to a high integrity forest. Wow, this looks really different on this computer. There's a lot of high integrity forest left, depending on quite how we define it. So all to play for in Central Africa. Next. So that's kind of where we are in the amount of forest. Now I want to talk about two things. How much carbon is removed by African tropical forests? About 1.5 billion tons a year, so about 4% of global emissions. And then this newish discovery about the Congo Basin, the peatlands in the Central Congo Basin. Next. So this figure that's been well used around the world about the amount of carbon being taken up by intact forests in the Congo Basin comes from these ground observations that Adriane talked about from the Congo Basin. We've also got them across Central Africa. So we work with lots of researchers, and the idea is that you have a patch of forest, every single tree has its diameter measured, is identified to species, which is a tough job in these really high species-rich forests, measure the height, then we can estimate how much carbon is stored in that hectare of forest. We can go back a few years later, re-measure them all, see which ones have died, which ones have grown, re-estimate the amount of carbon, and then we can tell you for that patch of forest whether it was taking carbon out of the atmosphere and getting bigger, or losing carbon to the atmosphere and the above ground biomass carbon storage is getting smaller. And we have this across the region going back around 25 years or so. Next. So these blue dots and the sizes show how many plots there are. So we have plots across the region. And it's those measurements that allow us to say with a reasonable confidence that these forests are a globally significant carbon sink. So this is like the background uptake, the natural sink. Next. And to put this in a global context, Rockstrom has put together this background sink in the oceans and on the land surface. And what we can see for the Central Congo, for the Central African region, is when you compile all this data, the African tropical forests are the most efficient natural carbon sink anywhere on Earth, both the land surface and the oceans included. So really important in terms of the climate. And I'll just say, echo what Adriane said, is we currently have no funding whatsoever to continue these measurements to tell you how big this sink will be going into the future. And this sink, unfortunately, we cannot really detect it from space because the amounts are very small and the biomass is very large in these intact forests. Next. So the Central Congo peatlands, muddy work, that's all I'll say. Next. So in the center of the Congo Basin is a huge wetland around the size of Germany. It's got a forest on top of it, and there's not that much known about it. And I had thought that perhaps where the flooding is happening all year round, where the water is at the surface, the decomposition might be slowed down enough that it doesn't go to completion, and there may be an accumulation of peat underneath the water in the soil. So I went there with my students and we and collaborators from the Republic of Congo, and we spent several years going into the peat swamps, going into the swamps and trying to find out what was there. Next. So this is typically what it looks like. All this reddish water is water. It looks a bit like Coca-Cola. It's got lots of tannins in it from these slow-growing trees. And it's got a short tropical forest on it. Some of the highest densities of elephants and gorillas in the world are in these peat swamp forests because there's very few people, very little human activity there. Next. And then we also find this very tall palm swamp forest. So you can see the colleague down at the bottom. So you can see how big these fronds can be, like 20 meters tall for an individual frond. Next. And underneath these two vegetation types, we find peat. So semi-decomposed plant matter that's very high carbon stock, up to around 6 meters deep. Next. So as we can't detect peat directly from space, we can use the association between where we find peat and the vegetation above, and where we don't find peat and the vegetation above, to use remote sensing, to use satellites, to estimate the area of peatland. What we find in our newest map, 16.7 million hectares of peatland, more than 30 centimeters deep, and that's about 15% more than we previously thought. Now we've done a lot more exploration in the Democratic Republic of Congo over the last 2 or 3 years. Next. And what we can also do now we have enough data is look at the associations between peat depth and environmental parameters. And that allows us to make a estimate of the amount of carbon for every single half hectare of peat swamp across the entire region. So what we can see is we find about a minimum of around 500 tons of carbon per hectare and going up to around 4,000 tons of carbon per hectare. That makes these ecosystems some of the most carbon-dense ecosystems on Earth. So there's almost as much carbon in these peatlands, covering a few percent of the Congo Basin, as there is in all the trees in the rest of the Congo Basin. It's that carbon dense. Next. And here's the slightly less good news. So these peatlands are pretty intact at the moment, but only around 8% of that carbon is in some kind of protected area. So there's a big job to keep this carbon protected. Next. So it's currently used by local people in a pretty sustainable manner. Young fish live in the peatlands and grow up there as young fish and then migrate out. So you can kind of think of these peatlands as giant fish farms. And that provides the protein for the local people, and it also provides a large amount of their income where they dry fish, smoke it, dry it, and then sell it on to markets further away. And clustered around are a series of threats. On the left from oil exploration, and on the right from logging concessions that haven't occurred yet, but they're inside concessions that overlay the peatlands, and a threat from oil palm plantations too. Next. And many of you have heard about the oil exploration licenses from the Democratic Republic of Congo. So we took those license areas and overlaid them with our peatland map. The peatland swamp is in yellow and the rainforest is in green. So about 1 million hectares of high carbon, high integrity peat swamp forest is within those concessions, and around 11 million hectares of tropical rainforest. Again, most of that high integrity. Next. And I just want to kind of get over how sensitive these peatlands are. So you have to keep peat wet to keep the carbon in the ground. And the trees are very sensitive to the length of the flooding season and the height of the flooding. And this is a picture from the 1987 in Central Africa. So you can see the road, and then you can see the light green is all swamp forest, and then you can see the logging camp to do logging on the dark green areas on the left, which is the terra firma forest. Next. And this is it in 2017. So the road, you can see the road and the logging camp, and now all the trees for as far on the flooded forest, as far as the eye can see, are now dead. And that's, we think this road was pure accident. This road changed the drainage and has killed all the trees. And that means there's no carbon input from the production of the trees, so there's going to be a lack of input to form new peat going forward. Next. So they're really, really sensitive to changes in terms of infrastructure. And there's one more change. So this is the work we published just before COP, where we have taken peat cores and dated them using radiocarbon dating. And what we see is the peatland in one area of the Republic of Congo began forming at least 17,500 years ago, maybe something like 20,000 years ago. And what we had was like very steep accumulation. There's lots of peat being produced, and the carbon is being taken out of the atmosphere. And then, around 7,000 years ago, almost stops. And then it races back up again. So we have this interval where there's hardly any peat production, or there was a huge amount of decomposition. And what we find when we analyze the peat from that depth is that it's so decomposed that it has a chemical structure almost like lignite, like brown coal, because it's super decomposed. And what we find is that from pollen that's preserved inside these peat cores as well, is that a forest stayed, but lots of the swamp forest species dropped out and were replaced by terra firma species in that time interval. Next. And the other super cool thing from a science perspective, and incredibly useful, is that when a plant lives, it produces waxes on its leaves. And those waxes can tell you about the rainfall at the time it was living. When the leaves die, the leaves decompose, but the leaf waxes do not decompose in the peat, even 20,000 years on. So we can analyze the chemical composition, the isotopes of those leaf waxes, and calculate what the rainfall was doing at the time it was living. So up is wetter, down is drier, and it was basically pretty wet, and then it got really, really dry in this red period, and then it stabilized, and then it got wetter again. And then this is the brown bar of where we lost peat. And what happened is it got really dry, And then it got so dry, at least 800 millimeters less rainfall than at the beginning, thousands of years before. And it got so dry that the peat started to decompose en masse. Because we have peat that's decomposed, all of this part, that's decomposed, that's older than when the drought started. So it's decomposing even older peat. This peat core of 6 meters, we lost at least 2 and potentially 4 meters of peat from this column. And we can see this same thing happening across the region. So what we see is that today, these peatlands are very, very close to a tipping point to releasing lots of carbon. Now, we don't quite know where that how close it is. It will be like 50 millimeters away or 200 millimeters of rainfall a year reduction away from it. But what we do know is that there's evidence over the last 20 years that one of the 2 dry seasons in the year has been getting longer in the Congo Basin. Now, we don't know whether that's going to persist, but some of the climate models show a drying, increases in droughts, and some of them don't. And there just isn't enough research done on this area to disentangle those 2 things. So this is a real live thing to watch, because there's 30 billion tons of carbon, 3 years worth of fossil fuel emissions in this peatland. And actually, this is one of the things that people from outside are doing that's affecting the peatlands, releasing carbon dioxide into the atmosphere, potentially driving droughts in the central Congo Basin. Next. And I hope that wasn't too depressing in week 2. I mean, I think it's all to play for. I genuinely believe that. I'm very happy to answer any questions. Thank you.
Yes, thank you, Simon. Quite mind-boggling. I've been trying to picture what 2 to 4 meters of peat multiplied by an area the size of Great Britain is. I mean, that's 2 meters, right? And Great Britain is a big place. I've been there. That's a lot of carbon back into the atmosphere. Quite an unsettling picture. Are there any questions? I hope so. I think we might have to run back and forth with this mic.
Thank you. That was brilliant. What do you mean by most efficient carbon sink? Can you elaborate on how you define that? Thank you.
Greatest carbon uptake per unit area. So per hectare. So it's taking up more per hectare than, so 100 meters by 100 meters than an equivalent patch of forest in the Amazon or in the boreal region, or an equivalent 100 meters by 100 meters of ocean.
Thanks, that was fascinating. Extension to that point, what's making it the most efficient? Thanks.
So I think what's making it more efficient than the other forests in the tropics is that the Congo Basin forests are on average at slightly higher altitude than the forests in the Amazon. So they're a tiny bit cooler, maybe about 1 degree cooler. They're also not quite warming as fast as some of the places in the Amazon. So I think that they're further away from an optimum temperature for photosynthesis, or they haven't gone over that point unlike in the Amazon. And we haven't seen the intensity of droughts in the Congo Basin as we've seen in parts of the Amazon. So I think that's the main answer. There's probably also a kind of biogeographic history part to it, in that the Amazon is, the Congo Basin has been through drier patches in its evolutionary history. So species are probably better adapted to potentially drier conditions.
Thanks. Yeah, agreed. Really, really interesting. I was going to ask, on a scale of not very important globally to extraordinarily, really, really very important globally, obviously this is just a case study for Congo, how important is peat as an issue, and then also how seriously is it being taken right now, and how do we make that more if it needs to be?
Peatlands overall are about 3% of the global land surface, and they're about 30% of the carbon that's in soil. That 3%, that carbon is about, let me get the stat right, I think it's about twice as much as all the carbon in all the vegetation of the world. So in terms of like action on keeping carbon out of the atmosphere, then that's a place to look. In terms of emissions, emissions from peatlands are around 5%, equivalent to 5% of global emissions from fossil fuel use. I mean, if you want the real like environmental horror story, Indonesia is the place to go. So there they had a program of draining peatlands to grow oil palm and fast-growing timber species for the pulp and paper industry. And in 1997-98, there was a strong El Nino drought, huge fires, and we can see it in the atmospheric record. Same 2015, also serious impacts of drought. And that 2015, which was much more, 2015-16 drought and fires were much better studied in terms of the people. And between around, I think it was 66 million people were negatively impacted in terms of their health from those forest fires, and a like big knock-on multi-billion-dollar impact on the economy. So Congo shouldn't go down that route. And in terms of it, like the peatlands have gone up the profile really rapidly. I was amazed that Joe Biden in his speech here last week said that we should be protecting the Congo forest and peatlands, which is pretty amazing given that we didn't really know they were there until the last few years. Well, not Joe Biden, but you know, his team.
Thanks very much, Simon, and thanks everyone for your questions. Okay, on to our third and final speaker. So, I'd like to welcome Nancy Harris, who, like Simon, also spoke last year at the High Integrity Science event at COP. She's very welcome back. Nancy is a forest ecologist at heart and is the research director of WRI's Global Forest Watch and the Land and Carbon Lab initiative. Through that, she works with companies, governments and civil society organisations to use WRI's monitoring data to mobilise more effective conservation, restoration and sustainable forest management strategies, providing decision makers with the information they need to address rising competition over the world's finite land. You give me a moment to arrange your slides, and away we go.
I'm going to walk over here just to give you all something else to look at, another vantage point here. So following Simon and Adriane are very tough acts to follow. As I'm going to use a quote from my colleague Francis Seymour. I feel, in comparison to those two, I am not a real scientist. I just play one on TV. This is my TV. So I'm going to talk a little bit about improving the estimates of the global forest carbon sink. We heard a lot about the Amazon basin forest. We heard a lot about the Congo basin forest. What is the overall global picture? So I have split this talk into two parts, if you want to advance the slide. Okay, so part one of this presentation is what do we know now about forest carbon removals globally, and then part two will be how can we improve those estimates. Go ahead. Okay, so last year, I think Adriane showed the same map, so I won't belabor it, but last year we published this map of forest carbon fluxes, both gross and net. using a combination of the University of Maryland Global Forest Change data that Simon showed in his Congo Basin map, combining that with emission and removal factors in an IPCC-style emissions reporting framework to estimate emissions and removals globally from 2001 to 19. That was the original paper. We've since updated that data through 2021. And what we can see in this map is we have carbon sinks of approximately 15.6 gross removals, gigatons of CO2 per year. Gross emissions have gone up since our original paper of 8.4 gigatons per year of emissions, leading to a net flux of negative 7.2 gigatons per year. And this is the first sort of map this is the first map that we've had of this type, right? And so the beauty of maps is that they are spatial by nature, which means that we can analyze any sort of polygon or area of interest that we're interested consistently using this map. Next slide. So I'm just going to show you an example of some analysis that we can do using this global data set for several of the indigenous people and local community lands across the Amazon rainforest. Those are those areas in gray. And so we can look at those areas, and we ask many people live in these areas. I think it's something like 385 different ethnic groups live in these areas. And if we look at what's happening within those indigenous people in local community lands versus outside of it, we estimate a net sink of 340 million tons of CO2 inside those gray areas. If we look outside, we have a net source of 250 million tons of CO2 per year. And so we always talk about the climate benefits and the climate regulation that these IPLC lands provide. This is sort of providing support to that statement. And next slide. And so you may be thinking, well, there's different areas of forest. Of course, those numbers are going to be different. And so we can also look at at those areas on a per hectare basis, and we can also split those areas up into emissions and removals, which are components of the net. And we see here from this figure, the gray bars are the IPLC lands, the white bars are outside. And it's really not anything to do with the net removals or the gross removals being any higher per hectare in these IPLC lands. The key point here is that those lands are really effective at limiting emissions, which is why the net flux is it's a stronger carbon sink in these areas. Next. And so we can look across these lands collectively, but we can also look at individual IPLC land regions or polygons. And we see that most of those areas are net sinks, but not all of them. So the net sinks are green, and the net sources are those purple areas. So the big purple down at the bottom is the Xingu tribes. Deforestation is encroaching into those areas and causing those to be net sources of carbon to the atmosphere. Next. Okay, I could go on and talk about that, but I promised you 2 parts. So I'm going to switch gears here and talk about how now we are trying to improve estimates, not just for the Amazon forest, but globally. Next. Okay, so the net flux map that I showed at the beginning, that is made up of an emissions map and a removals map. So here's the removals map, and I'm going to be the first person to admit that this is not a very sophisticated map. This is basically just using some sort of paint-by-number approach to apply default values to different forest types around the world. It's a little bit more complicated than that, but that is sort of the basic idea. So if you go to the next slide, this is an example, particularly for tropical forests, of the default values that are in IPCC guidelines. These are the updated 2019 numbers. And a lot of these defaults come from plots like Simon showed, like Adriane showed, where we have different default net biomass growth numbers for natural forests in different age classes and different continents and ecozones. And you can see there's only 3 age classes. It's primary, it's less than 20 years, and it's greater than 20 years per continent and ecozone. And so that's a good start, but we can probably do better than that. So next slide. And so I think Adriane, or maybe it was you, alluded to this problem of, well, why can't we just use satellites to monitor forest carbon removals? Well, the emissions are relatively easy, right? We can see a signal in the tree cover loss satellite. That is a signal, and there's a large drop in biomass as a result. So those are strong signals. With removal, those are a lot harder. So we have biomass gradually increasing every year. As Simon mentioned, sometimes it even decreases. And so if you go to the next slide, our annual increment in those biomass measurements is maybe 1%, if we're lucky, of the total stock. And so if we look at if we look at the biomass maps, the global biomass maps that we tend to have, the uncertainty bars are not 1%, right? They're something like 20%. And so trying to capture that increment within a large uncertainty bar is tricky. And so we're really trying to capture a small change in a very large stock. Next. So when we're thinking about how to improve these default numbers, it's like, okay, let's just go back to plots. Let's forget maps for a minute. And as Simon pointed out, there are lots of plots like this where people are hand measuring trees every so often and calculating things like this here on your left, where we have a number of trees by a diameter class. We have a basal area, or sort of a proxy for biomass, per diameter class. Next. And so where are these plots in the world? Well, Simon, you were part of the study, I think. So the Global Forest Biodiversity Initiative compiled more than 750,000 of permanent remeasured plot samples across 44 countries. This was a publication that came out in 2016. So measuring more than 30 million trees across more than 8,000 species. And these data were collected and compiled by by 92 organizations and institutions. Just a massive effort of human labor measuring these plots. Next. But, actually go back one. But you can see the distribution of where these remeasured plots are. What's missing here? So if you go to the next slide, Global South is missing. And so over the last 2 years, this team has really made a concerted effort to try to compile and collate more plots from the Global South. And some of them are remeasured, not all of them. And I will talk about that and what to do about that in a minute. So next. Okay, so I don't think I need to educate this crowd because Simon and Adriane already talked about this, but you have 2 inventory periods and you can calculate upgrowth, recruitment, and mortality between those 2 inventory periods based on the measurements of the trees that you're collecting. Next. And so we can look, using sort of machine learning models, we can look at which covariates are influencing those rates of upgrowth, recruitment, and mortality. So the dominant, strongest predictor of both upgrowth and mortality tends to be diameter. So the diameter that you were the last inventory is a good predictor of the diameter that you will be in the next inventory. And then the best predictor of recruitment tends to be tree diversity, tree size diversity. In addition to many other variables, topographic variables, Simon talked a lot about drought, annual aridity indexes. Those all play roles that are very complicated to tease out. And so by using some of these non-parametric machine learning models, we can sort of start to correlate the variables with what's happening at the plot level. Next. Okay, so the premise here is that we can use these models to predict what's going to happen at the next inventory. And so if we have plot data from 2 inventories, we can predict what's happening at that next inventory on the left, and then we can use data that the model has never seen before to validate those biomass changes for a given forest type of the world. Next. Okay, so all of that was sort of a long-winded way of saying this sort of approach can give us a new training data set for a machine learning model that does the spatial part. So if we can do the temporal part on the plots, that can act as the new training data that we use our sort of typical spatial wall-to-wall modeling methods with. Next. Okay, so go back. So I was trying to anticipate questions, and one question is, well, those yellow plots, they don't have multiple inventories. What are we going to do about those, right? So the next slide just shows that a lot of these, hey Tom. So the next slide just shows that there are a lot of these models that have been developed for different, almost all kinds of forests in the world, where if we don't have remeasured data, the parameters of upgrowth, mortality, recruitment can be used from those published numbers and fed into this kind of modeling. Next. Okay, so just very clearly reiterate, we do the time part first at the plot level, forget the maps, and then we bring the maps in where we're modeling change over time. Next. Okay, so I really wish we had a prototype for a tropical forest, since this is the topic of this session, but we're not there yet. That is the goal that hopefully we can achieve, but we do have a prototype for the US. In the northern forests of the US, we have a very strong inventory program in the United States that has a lot of inventory plot data. And so let's see how this sort of approach works for a test area. And so this prototype was developed, a model was developed using only the plot data from the state of Indiana, which is in this yellow boundary. And then let's use that data to predict biomass growth over the entire green area and see how we do. Next. And so the results of that exercise look pretty good. We can compare the observed values from plots that never have seen, the model has not seen before, versus what we're predicting over across all those plots. And then the next slide, or if you click next, the model is performing about 50% better than the standard model used by the Forest Service called FVS, Forest Vegetation Simulator. So at least for northern forests, this approach is working. So the next question is, well, the US has a lot of plots. Maybe this is why it's working there. And so that is sort of an open question. Next. And then the beauty of this approach is that we have multiple inventory periods, but we can use the modeling to either project backwards or forwards in time. And so as we project forward, it becomes more uncertain, but we do have information about different species and different size class distributions, different forest types, where we can look at, well, under different climate change scenarios, how are these dynamics going to change over time? So that in this example, you can't really see the unit here. It's basal area, which is sort of a proxy for biomass change. So under a constant climate, those forests in Maine are losing biomass over time, and the Midwestern forests are gaining forests over time. Under climate change scenarios, those Maine forests are actually losing or gaining biomass. So as it's getting warmer, growing conditions are getting better in Maine. Next. Okay, so this is a brand new project. We have not really started it yet. So the milestones for this project is to finish the US, and then as we build out this global model. And so we'll have a prototype hopefully sometime next year if we're on track, and then a final global map in early 2024. Next. Okay, key takeaways. The current location and future direction of the global forest carbon sink are very uncertain and continue to be. And then the maps like the one I showed are really useful, especially in a policy context, for understanding carbon dynamics at multiple scales and within specific forest extents. And as I mentioned, separating that signal of long-term forest carbon removals from the noise of uncertainty, that remains a challenge for a lot of different remote sensing approaches. And so we're trying something different. We don't know if it's going to work, but new data-driven approaches are underway to monitor the global forest carbon dynamics and to develop those projections over time under different climate change scenarios. I don't know why the text changed down here, but if this does pan out, then these results are really going to be useful to start to explore trade-offs between different ecological and economic objectives, and hopefully benefit forest management decision making. Any questions?
Thanks, that's great. I'm curious though, because your map, the big global map shows figures for forest production where, forest has been cleared. I was looking at Europe particularly. It would be lovely if it was all that forest, but I just wonder how you deal with that where land use, has changed and forest has been cleared often millennia ago.
That's an excellent question. So in this approach, I think we're going to try it only for undisturbed forests because there are a lot of land use change dynamics that this kind of modeling approach is not going to pick up. And so we're really focused on the sort of intact forests, the forests that have not been disturbed for a long time, to model the removal rates there. And we'll see about these other secondary forests if this works.
Thanks. Just wanted to ask about the data going forward with the new monitoring. So obviously you have people with tape measures on trees and you have satellites which are only so good and presumably getting better but still only so good. I was wondering, presumably like Internet of Things and AI sort of driven stuff is the next step. I wonder how far away you think that is from being useful on a large scale, or whether that's still, we're not there yet.
This is AI. So we're using AI machine learning for correlating the variables to the plot increase, and then we're using other AI models for creating the geospatial predictions. And so, yeah, those approaches are also improving over time. And so, in the geospatial mapping part, there are several different models that we can try. And we will probably use some sort of ensemble modeling, solution that takes the best of, all of these different machine learning models, the statistical models. We put them all together and see what we can put together. Did you have a question?
If you look at, say, IPCC Working Group 1 report, then you see the trajectories of the carbon sink going forward. And they're all positive, and it depends on the rate of emissions. And they're not hugely different amongst quite different scenarios going forward. So that's my kind of like background, like that's the rough trajectory. And the concern, and my concern, and where I differ from those dynamic global vegetation models, is that things could change more quickly, and systems might be more brittle than you kind of see from these global figures. And I wonder how your model deals with things like rapid change of species, because you've got basal area at one point and then a few years later, and that's basically the change that you've got. So you haven't got any of those non-linearities or those changes in species, which is kind of, in my view, the kind of scientifically interesting bit, but also the bit that's valuable to society to bring to the table.
Yeah, started this work not necessarily thinking of the projections. We have these average long-term 20-year removal rates from 2000 to 2020 as our map. And so the goal was to do something that we could model the annual change in biomass, not necessarily for the future, but for now, to combine with our emissions map. But in the projections, it is very nice when we have all of that information on the species and the size distributions. Like, we will be seeing some of these species change, and it depends on how we design the model, how detailed we are being with how we group the species, and so we have a lot of things to still figure out about that. But
so in the beginning, you showed that the increment of the change in terms of growth is small, and with plots, you need to look at it over a long period of time to even detect that. Mapping biomass has uncertainty, so it won't do it. Now, with this data, you showed also a lot of uncertainty. The RMSE was high. So wouldn't that also have the same problem of not being able to predict what the future is?
yeah, it's like, well, do you do the spatial part first or the temporal part first? Is it going to make any difference if you do the time first versus the space first? We'll see, yeah. But if we're thinking about making a biomass change model, then it's, in my opinion, good to use some sort of change training data to make the map. You guys, I'm holding you back from, there was wine over there before.
Thanks very much, Nancy. Can you join me again in thanking all three of the speakers with a rousing round of applause? I'm going to keep your attention for just one more minute before I let you loose on the snacks and drinks, which have been waiting for us over there. Just trying to sum up very briefly some of the key points we've heard from these three talks, which have been, I think you've seen, have had a lot of commonalities and also pointed to some areas of active research and active discussion. I think one of the key things to take away is the scale of these processes that we're looking at in high integrity forests around the world is very large, and in response to one of the questions from the floor, is material to global change. Very important that we recognise what is already known, what has been learned over the last 10 or 20 years of large-scale research in this area. And then in parallel with that, to recognise that this is still a very active area of research, and there's a lot more still to understand, both about what's going on now and about how things might evolve into the future. These processes are quite variable both in space and in time. The differences are driven both by natural factors and by all sorts of human activities, both on the ground and through impacts on the climate itself. And finally, I think it's very important to take away the point that many of the speakers showed in the way they presented the data, that we should look beyond the net results of things and really try to understand and unpack what's going on, both in terms of the processes driving gains in ecosystems and the processes driving losses, because they can be driven by very different parts of the global socio-economic system, and we need to understand them all if we're going to keep these forests doing all they do for us and for the biosphere. So on that note, I will free you to go and fight over the food. Thank you very much.